Hi guys, welcome to the next lecture. Today I shall be talking about exponential functions. First recall, if b is a non-zero real number, then non-zero integer power of b are defined by b to the power n, say, which would essentially mean that I am multiplying b by itself n number of times. So how many times have I multiplied b? N number of times. N times, right? Now we can even define b to the power minus n. B to the power minus n is basically 1 upon b to the power n. So what you're doing is 1 upon b is getting multiplied by itself in the denominator n number of times, right? If n is 0, then clearly b to the power 0 is what we are looking at. And that's going to be 1. We can even actually define this power for some rational, say p by q is a positive rational number. So p by q belongs to q plus. Then b to the power p by q can also be defined. And that essentially would mean that you're taking the qth root of b to the power p. You're taking the qth root of b to the power p, right? Now, this is same as saying that you are taking the qth root of b, and then you take the power p. In any way you do it, you're basically looking at b to the power p by q. Similarly, you can define, the way you define b to the power minus n, you can define b to the power minus p by q, and that's going to be 1 upon b to the power p by q, right? Now, there must be one particular question coming to your head, and that is, what if b itself is negative? In case b itself is negative, the fractional powers of b, they can be non-real. How? Basically, if b is negative, then, if you take some fractional power of b, it can give you imaginary values. For example, minus 2 to the power 1 by 2. That is the square root of minus 2. Clearly, the square root of minus 2 will not be a real value. It's an imaginary value. So to avoid this complication, we will assume throughout in our discussion that b is a positive number. Let's assume that base b is greater than 0 so that we do not face any complication. With positive base b, we can define even irrational power. So you see what I'm trying to give you an algebraic intuition to powers here. So we are first, just starting with base b, some integer power n. That's the simplest thing. If I can look at b to the power n, I can even look at b to the power minus n. Then we spoke about b to the power 0. What if this number is 0? The power is 0. I will get just 1. Then I'm talking about rationals. If the power is rational, we can easily figure it out. And this is what it will look like. Yes, you can have a negative rational as well. That will show up as b to the power minus p by q. And we do know how to define it. But when b is negative, we might not get a real value as an outcome. And that is why we will, in our discussion, avoid the base b to be negative. We will assume positive base. With positive base, we can even define powers in terms of irrational numbers. So, for example, 2 to the power pi, 3 to the power root 2, pi to the power root 7. So minus root 7 or root 7. So we have irrational numbers in the powers, if you see here, right? These are just certain examples. You can define them. One approach could be, let me just take you through this table. Suppose we are taking 2 to the power pi. Now I know that pi is a fixed value. Pi is a fixed value, 3.1415926, so on and so forth. The decimal never ends. We're stopping till 6 here. Okay, now let me define x and 2 to the power x. Since we are talking about 2 to the power pi, what I'm going to do is I'm going to take a sequence of these rational numbers. Sequence of rational number. So this x that I'm taking, it's basically a sequence of rational numbers. So I will be writing 3.14, one by one. So I'll start with 3, then 3.1, 3.14, so on and so forth. So as a sequence of rationals, I'm going to write it. Okay, and then I'm going to get the power of 2 with this sequence. So I will get a sequence of rational powers. With the sequence of rational, I will get sequence of rational powers of 2. So you will get 2 to the power 3, very simple, 8. 2 to the power 3.1, when I'm taking x as 3.1, 2 to the power 3.1. Use your calculator and you will find that the value is 8.574188. If you increase it to 3.14, the power 2 to the power 3.14 will give you 8.815241. 3.141 will give you 8.821353. With 3.1415, you will get 8.824962, and so on and so forth. So if you notice here, what's happening? As you're changing these rational powers, you are getting 2 to the power of whatever rational you are taking. What you must notice is that as these rationals, these exponents actually, 2 to the power, the power that we are taking, as it is going towards pi, as the value is going towards pi, can you see that the sequence of the power 2 to the power is also approaching, one particular number? It is almost, if you notice later on, it's just almost approaching. It is almost approaching 8.825. So with this notion for irrational powers, we can actually say that we are able to find these, we can even find out to a base b, if you take an irrational power, you can actually figure out what the power would turn out to be. Okay. So just the way we are able to actually figure out even irrational power of, any base, like we have 2 to the power pi, we can actually figure out certain laws associated to exponents. Following are the common laws that we use. B to the power p multiplied by b to the power q. When the base is same and you have different powers, you can take the base same and add the powers. So that could be done. Similarly, if you have that in a division form, b to the power p upon b to the power q, this will be b to the power p minus q. If you have b to the power p whole to the power q, that means the power is actually getting multiplied. So you just have pq as the power. Now here I would like to now further mention the family of exponential functions. What do you mean by family of exponential functions? So a function of the form fx equals to b to the power x, where base b is greater than 0, is called an exponential function with base b. What about the functions like x to the power 2, x to the power pi? Are these also exponential functions? The answer is no. This is a polynomial. This is some power of x. Yeah, when you're talking about an exponential function, you have a fixed base. The power is the variable. And that's how the family of exponential function gets created. For example, you can have, say, fx equals to 2 to the power x. Now, with different x's, you can create you'll have a particular graph. Fx equals to half to the power x. With different x, you can create a graph. Similarly, you can have pi to the power x for that matter. When base is fixed and variable is in the power, that's an exponential function. That's what an exponential function is all about. Let me just now talk a little bit about the graph and its properties. Y is equal to b to the power x is our exponential function. The graph definitely passes through 0, 1 for a simple reason, because b to the power 0 is equal to 1. Any base b to the power 0 will give you 1. So, of course, the graph has to pass through 0, 1. Now, if your base b is strictly greater than 1, the value of b to the power x would definitely increases as x increases. Next point, that if b, your base, is between 0 to 1, what will happen to b to the power x? No matter what value of x you will put, you would get the value b to the power x as a decreasing one as x increases. So the value of b to the power x decreases as x increases. Because you're talking about a fraction between 0 to 1. That's your base. And then you're taking power. Now, no matter what is in the power, as you increase the value of what you have in the power, the value of b to the power x would actually decrease. Next point to notice, if your base is equal to 1, then the value of bx is definitely a constant. It's going to be just, 1 is constant. So that's about b to the power x as you think of different bases. What we just spoke about, let me just give you a graphical interpretation of that. So this is your x-axis, and I've created these, this dotted line is there at 1, and these two graphs are there. Can you think of what's happening here? What graphs are these? Well, this dotted line that you see, a constant, you're just getting the value 1. When is it happening? When your base is 1. So your function y is 1 to the power x. That means it's just 1, right? Now let me take you through this graph. Clearly, here the values are increasing. This is the graph of y equals to b to the power x, where b is greater than 1. It's an increasing graph as x increases. So that's what is happening here. On the other hand, can you see this decreasing graph? This decreasing graph is again y equals to b to the power x, but when b is a fraction between 0 to 1, it's decreasing in x. What you must notice out here is all the three graphs meet here. And this point is 0, 1. Y is equal to 1 and x equals to 0. And that's going to happen in all the three cases. That's happening, right? So they will meet out here. So I wanted to talk to you about what is a family of exponential functions. So when I say family of exponential functions, what do I mean? So suppose we talk about y equals to b to the power x. Now with different b, I can create a set of, b to the power x. For example, a function where I take b as 2 to the power x. This will be one particular function because with different values of x, I will be generating a graph of this. With 3 to the power x, I'll get another graph. With 1/2 to the power x, I'll get one graph. with 1 by 3 to the power x, I'll get another graph. So what are these? These are all these graphs are part of the family. Which family? B to the power x family. So here I've taken up a sample. I generated these graphs. So can you see this red color graph that you can notice here? This is 2 to the power x graph. This blue color graph that you notice here is 3 to the power x graph. Can you see these are increasing graphs? Now, this red color graph that you see here is 1 by 3 to the power x graph, and this is half to the power x graph. These were just some values that I took. You can take different bases, and you can create the entire family as much as possible. You can create a big family of these graphs. This is what is family of exponential functions. If b is greater than 0 and b is not equal to 1, then point number 1 that you must note, the function fx equals to b to the power x is defined for all real values of x. So its natural domain would become minus infinity to infinity. And on the other hand, the function b to the power x is continuous. Number 1, it's continuous on the interval minus infinity to infinity. And its range is the outcome that you will get. Can you see in these graphs, what is the kind of outcome that you're getting? Your y is always positive. So which means the range is from 0 to infinity. And it's approaching 0. It's never equal to 0. It's approaching 0. So therefore, open 0 to infinity. Let's work on a problem together. Find the domain and range of fx equals to 1 minus 2 to the power x. Let's go step by step here. Let us first consider y equals to 2 to the power x. Look at it graphically. What will you get? The kind of graph that you will get, 0, 1 is where it will intersect. It will be a point on the graph. So it's going to look like something of this sort, okay? So y equals to 2 to the power x. I am interested in y equal to minus 2 to the power x. Y equal to minus 2 to the power x, you can get it by taking the reflection of this graph. If you take the reflect this graph across the x-axis, you will get minus 2 to the power x, right? So that's going to be something of this sort. Suppose this is your x-axis. Reflection means you will get minus 1. It's going to intersect somewhere at minus 1, coming like this. So sort of a reflection you can see here. Okay. This is y equals to minus 2 to the power x. And now what are you interested in? You're interested in 1 minus. Y equals to 1 minus 2 to the power x. That means you're adding 1 to this graph. So when you add 1 to the graph of minus 2 to the power x, what will happen? The point which meant minus 1 for you, y equal to minus 1, will now be 0. So the graph shifts up. X-axis, what was x-axis for us in y equals to minus 2 to the power x? The role will be played by y equal to 1. Okay. And there is this shift, upward shift, right? So this is what the graph will look like. Now talking about the domain and range of this function. So graphically, if you've understood what will be the domain and range, pause here and try to write it down yourself. Can you say what kind of x's are we taking up? We are taking all the x's from minus infinity to infinity into consideration while graphing it, right? Can you say what kind of y's are being generated? Yes, the y's are not going in any time above 1. So that means I can get minus infinity. I can get minus infinity somewhere down there till 1. But it's never reaching 1 and it's never going beyond 1. So that's going to be the range of it. Now I'm going to talk about a very special base for exponential function, which is called e. It's a special base. It has a fixed value, 2.7, approximately 2.71882. Again, it's an irrational number, which will keep on going this decimal. If x equals to e to the power x is actually called natural exponential function. Like you have natural log, natural exponential. Why did I call it special? There's a reason behind it, why it is special. It is special because it is the only base for which the slope of the tangent line to the curve y equals to b to the power x at any point p on the curve is equal to the y coordinate at p. For example, if we take y equals to e to the power x, then at the point 0, 1, the slope is actually 1. The graph would go something of this sort. This is y-axis, this is x-axis. At 1, you will have this. And if you notice what is the slope at this point, the slope is a 45-degree line. Yeah. Slope is 1. Hence, it has a lot of consequences in calculus, which is something that I will talk about later when we are working on calculus, specifically with these kind of functions. Now, connecting exponentials and logarithm. I've already taken a lecture on logarithm. Now, in logarithm, what do? We are talking about taking log with base b, x, right? Log b with base, b is the base, x. It basically means, whatever it turns out to be, basically it means that b is the base, and when you take some power, which is log bx, this is the power that you've taken, and you get x. You get x. X is that power that you take, which, x is that power that you take, which gives you this result, right? So if b is greater than 0 and b is not equal to 1, then b to the power x and log bx, log base b, x, log of x with base b are basically inverse functions, if you notice, are inverse functions. The keynotes that I want you to write down right now. The graphs of y equals to b to the power x and y equal to log of x with base b are reflections of one another about the line y equals to x. The most important logarithm function in applications is one with base e, which is the natural exponential, as we say, and we call this logarithm function with base e natural logarithm. The exponential function and logarithm function, these are two functions which are very important when we are working on the prospect of growth. It could be growth related to anything. So there's something called exponential growth. There's something called logarithmic growth. Okay. To give you a perspective into it, I will just actually pick up the functions e to the power x and log x, the natural log x, with the help of values of x that I give. Let's see what kind of generation happens. So suppose x is 1. E to the power x is basically e has a value 2.72 approximately, right? So let's take the power of that. If you take the power of that as 1, you will get 2.72. And log of 1, when I put the value 1 for natural log, I will get 0, right? So there's no growth. 2, when x is equal to 2, you take the power 2 basically of 2.72, you will get 7.39. Do you see the kind of jump we have here in this exponential growth? Log of 2, on the other hand, is 0.69, a very slow growth. Just a minute change from 0 to 0.69. Still, there is a change. There is an increase. When x is 3, e to the power x will give you 20.09. Again, a huge leap. When in log, I put log 3. Log of 3 is 1.1, around 1.1. Very slow growth, but yes, there has been a growth. When x is 4, exponential is giving me 54.6. E to the power x gives me 54.6. Again, it's more than doubling up. It's like almost tripling up. On the other hand, log of 4 is 1.39. And so on and so forth. Just see what's happening when I reach x equals to 10. 22,026.4 is what I get as EX. On the other hand, log x, log of 10, 2.3. Look at when x is 100. I have something multiplied by 10 to the power 43. And when it is 1,000, 10 to the power 434. That's what exponential growth is all about. The kind of multiplication that is happening is humongous. Though there is an increase in logarithm also, there is an increase, but it's a very slow increase. Whatsoever, there are certain limits. I've not touched upon the topic of limits because I have not started calculus with you guys yet. But when we talk about these growths, so we are talking about where are we approaching. So the concept of approaching is something that I'm using here. Limit is the concept which is associated to approaching. So x, as x is approaching minus infinity, e to the power x is almost 0. It's almost 0. Log, since these are invertible, right? So as log is going to 0 plus, log x is actually minus infinity. Similarly, as limit x goes to plus infinity, e to the power x gives you plus infinity. And as x tends to, x is approaching plus infinity, e log of x also gives you plus infinity only. But the only difference is there is a very slow movement when it comes to log, and there is a very, very heavy movement, jumps when it comes to exponential growth. I hope certain concepts of logarithm and exponential would be clear by now. Thank you for watching.